Okay, this question is about structural isomers shown P, Q, R, S, T, and U. Part A, identify the isomers that would react when warmed with acidified potassium dichromate. So that's an oxidizing mixture. State the expected observation when potassium dichromate reacts with these isomers. Okay, so acidified potassium dichromate will react with primary and secondary alcohols, but also with aldehydes. So I'm just going to go through and have a look at these. Well, this one is an aldehyde, so it will definitely react with T. That one's a ketone, so it won't react with that. The other four are alcohols, but I do need to classify these alcohols to make sure that they're not tertiary. This one is tertiary, this one is primary, this one is secondary, and this one is secondary as well. So it won't react with U, it won't react with P. So the isomers Q, R, S, and T are the ones that it will react with. So let me just rub those out now that I've got those. Okay, I'll leave those on so I know that those are the ones that it will react with. The observation, so acidified potassium dichromate goes from orange to green. And then with Tollens reagent, so Tollens reagent or an aldehyde, the only one that is an aldehyde is T, so isomer T, and then the expected observation, silver mirror or precipitate. Okay, so see, I'm going to have to keep going back to these at the beginning of the question to have a look at these. Separate samples of each isomer was warmed with ethanoic acid, so that's a carboxylic acid, and some concentrated sulfuric acid. It's then poured into a mixture of sodium hydrogen carbonate. So this is the esterification reaction. So looking at making esters here, and to make an ester we need a carboxylic acid and we also need an alcohol. So all of the alcohols in the diagram above will react. So that's P, Q, R, and S. So P, Q, R, and S. So they're all going to make esters. So I've identified the monomers. Simple way to detect. So the simplest way is to smell it, and it will be sweet smelling. And remember the sodium hydrogen carbonate is there to neutralise any unreacted ethanoic acid and the concentrated sulfuric acid. And then give a reason. So C, give a reason why this it's put into the sodium hydrogen carbonate to react or neutralise excess. Okay, part D, type of structural isomerism shown by P, Q, R, and S. So P, Q, R, and S. So we've got the same basic structure, but you can see that the OH is basically changing position around all of these. So this is a position isomer. And then part E, describe fully how infrared spectra can be used to distinguish between R, S, and T. So R, S, and T. Let me rub everything else out so that we're not getting muddled up with it all. So I need to compare these two. So the easy one for T, so T has got a carbonyl peak, and I'll look that up on the data sheet in a minute. So R and S are going to be a bit more difficult because they're both going to have the OH alcohol peaks, and I'll look that up in a minute as well. Remember, you can have OH peaks that are carboxylic acid, so you need to state that you're looking at the alcohol. So there's nothing else in R and S that's going to allow me to distinguish it. So I'm going to have to use the fingerprint region for those two and then have that looked up in a database, okay? So let's go through these then. So R and S will have an OH peak. So if you just put OH peak, you won't get the mark here. And that's at 3230 to 350. You must always quote the data sheet. T is have a carbonyl peak, and then again that will be at 1680 to 1650. So those two are easy to identify between. So you can identify T from R and S, but R and S are going to be more difficult to distinguish. So for R and S, you need to use the fingerprint region. Remember, that's below 1500. And remember, these are unique to that molecule. That's why they call it the fingerprint region. But then you need to compare it to a database to find out which one it is. Okay. Statewide mass spectrometer using electrospray ionisation is not a suitable method to distinguish between these isomers. Remember, electrospray ionisation doesn't fragment the molecule, so you're going to get no fragments here. You're just going to get MR plus 1, so MRH. And because they're all structural isomers, they're all going to have the same MR, so they'll all have the same MH peak or MZ peak when we do the MR. So all the same MR, therefore the MH plus is going to be the same. Therefore, the MZ peak will be the same as well.